Okay, so let's start. Hello, everyone. My name is Miguel. I'm from LEAP, and I'm here today to introduce you again to this initiative, which is a joint webinar series between BigHPC project and the UT Austin Portugal program. I take this moment to thank you all for your participation in this session. In this webinar, we will welcome Amit, Ruhela, Cazes, Saran, Sangamithra, Goutham, and Stephen Harrell from Texas Advanced Computing Center, who will talk about experiments in implementing the BigHPC Virtual Manager. Let me take a brief introduction of our speakers. Starting from Amit. Amit Ruhela works as a researcher associate in HPC group at TACC Austin. He has earned his PhD degree in computer science from IIT Delhi and postdoc experience from the Ohio State University. His research interests are focused on feature and performance enhancements in MPI communication through novel and innovative designs. Regarding Cazes, which is the PI of this project, Cazes serves as the director of high performance computing group at TACC. He has over 20 years of experience in high performance computing in public and private industry. Dr. Cazes relies on his background in HPC, astrophysics, and climate weather ocean modeling to support the wide variety of researchers on TACC resources. His primary research interests are parallel I/O and advanced architectures. Then we also have Saran as a speaker in this webinar. Saran is a second-year computer science master's student at UT Austin. Is collaborating with TACC as a research assistant to build the virtual manager for the BigHPC project. Alongside with previously presented speakers, we have also Sangamithra Goutham, which is a second-year master's student at University of Texas at Austin. She worked at Systems and Storage Lab at UT as a graduate research assistant and has previously completed her 5-year integrated master degree at College of Engineering, Indiana University. Our fifth speaker, as I mentioned before, is Stephen. Stephen Leon Harrell is an engineering scientist at Texas University Advanced Computing Center in HPC Performance and Architectures Group. His research interests include performance portability, performance modeling, benchmarking, and HPC metric capture. As I mentioned earlier, my name is Miguel and I will be the moderator for this session. I would like to inform you that you can interact during the presentation. To do so, you can use the chat to share your questions. During the presentation, there are no discussion moments, but at the end of the webinar, we will provide some minutes to discuss all the questions and interact directly with you. I'll be monitoring the chat activity, ensuring that all questions are dealt with by speakers at the right time. Please keep your microphone muted during the session to prevent background noises, and let me inform you that the session will be recorded and you will have access to it in the end. Now we move to the presentations. So I'll kindly ask our first speaker to share his screen. Again, thank you very much for joining this session. Amit, the screen is yours. Please start.
Okay. Thanks, Miguel, for the nice introduction, and good morning and good afternoon, everyone. My name is Amit Ruhela, and I am a researcher at Texas Advanced Computing Center. Along with me, Stephen Leon Harrell and John Cazes, both from Texas Advanced Computing Center, are here for presenting this webinar. Apart from that, we have Sangamithra Goutham and Saran from University of Texas at Austin, who are students and who will be part of this presentation. The title of our today's presentation is Experiments in Implementing the BigHPC Virtual Manager. So outline of this presentation is, first we'll set the background. Basically, we'll explain what is HPC, what is big data, and how they are related to each other. Then the main focus of this presentation is virtualization manager. We'll explain what is it and how we have what options or what features we have explored for virtualization managers to design it. And this will be presented by Sangamithra Goutham. And then we'll speak about what are the issues with those designs, and how we come up with our own design. That will be covered by Saran. And last, Stephen will present the current state of the project and what are the future activities that we plan to do in the future. So let's start with HPC, big data, and their relation. So what is high performance computing? High performance computing is anything which requires a lot of computations, and then those computations are done on hundreds to thousands of tightly connected servers. These servers are called compute nodes, and as an example, we have shown on the right hand side. This is a picture of Frontera system, which consists of racks, several aisles of racks containing several compute nodes. And these compute nodes are connected through each other with the cables, which is shown in the bottom of the picture. And then these compute nodes together try to solve a variety of problems by thousands of researchers who runs distinct applications. Some of these traditional HPC applications that run on our systems are basically weather and climate applications that studies how hurricane comes or how they impact the lives of the people, how like study of tornadoes, ice sheet melting, and forecasting the weather or climate in next subsequent years or days. Then there are astronomy or cosmology applications, and then we have engineering applications or applications which studies the design of Formula One cars or rockets for space expeditions, etc. Apart from that, there are molecular dynamic applications, which basically looks at how the cells are made, like their atoms or molecules, how do they interact with each other, and how the viruses, just like the case of coronavirus, how do they, what are the characteristics of those viruses, their designs, and then there are other applications which basically looks for what kind of medicines fit for those viruses. Then there are applications which are basically the design of semiconductor applications, of study the materials required for those those semiconductors. And then there are some battery designs which basically comes under the material sciences. Last, there are other applications which are basically the earthquake applications, studying the earthquake characteristics and looking at the mining and drilling for oil and gas expeditions. So if we take a look at big data, they are not very different from the traditional applications. They just have a requirement which is distinct from the HPC applications. And the requirement is basically they deal with a lot of data or a lot of files. And any application which goes through or which generates or processes gigabytes or several terabytes of data, or even more than that. So those applications come under the big data category. And big data category or this domain has become popular with the rise of machine learning requirements. And these machine learning requirements, they try to solve all problems in a newer ways. Some of the examples are solar cell energy predictions or accelerating calculations for protein folding, etc. Now, these machine learning applications, they also perform some kind of predictions. They study the hundreds or thousands of images. They understand those images, find out the patterns, and then they make some kind of predictions. And the data comes from variety of hardware or variety of resources, for example, telescopes, MRIs, and even the people. So there are some applications which basically studies how earthquake displacement impact the buildings or cities, etc. Big data applications were also popular traditionally, which basically require a lot of computational research. For example, data assimilation applications, which combines the data from multiple resources and then study the current state and look for the future. Epidemiology is another kind of big data application domain where where the goal is to study how the virus is spread among the populations or disease spread among the populations, and data is collected through people, through the social media, or it could be also collected from the government or private resources. Last, there are drug discovery applications, which comes under big data category, and the goal is to combine or goal is to find out the best compound to which basically tries to provide solutions for different kind of diseases. Now, HPC and big data applications, there are several challenges in supporting HPC and big data applications. And basically the big data software and workloads, they don't fit together in HPC environment. The reason is HPC environment basically expect the regular and predictable IO, which is basically infrequent small read and writes. However, big data and machine learning workloads have irregular IO. They are mostly random, frequent, small read and write, and they have a huge amount of accesses for smaller files, which basically hurt the HPC systems, which has a large number of resources, but they are shared among the users, and it's always possible that some user might abuse the system, writing a lot of, when running the big data applications, writing or reading a lot of files, and impacting the performance of other applications. So then we have HPC applications. HPC basically expects softwares to be more or less like portable. They have very small set of run script or script files, which basically runs those applications on a variety of hardware. But on the other hand, big data and machine learning applications, they are very complex. They are very specialized. They run on some specific set of hardwares, and they are too rigid to utilize the system hardware in HPC systems. Then HPC expect workloads to share a system with distinct various other workloads, because HPC systems are pretty large. They are used by hundreds of users every day. So they expect workloads to be shared, and workloads to share a system, and all the users work collectively on those resources to solve their respective problems without hurting each other. However, big data and machine learning workloads, they expect exclusive access to the system. The reason is they often require privileged access, and they have irregular workloads, which is basically demands the unpredictable resources. And they also demand the persistent services, for example, databases and web servers running behind the actual big data workloads. So big HPC is a consortium of several institutions, and the goal is to provide a management infrastructure which basically composed of 3 components to address the challenges or to address the issues in running the big data applications on HPC systems. Big HPC consists of, the first component is the monitoring backend, which basically monitors what workloads are being running, what resources they are being using, and what is the usage of those what is the usage of resources for those workloads. So basically facilitates the quality of service for shared resources, for example, node, network, input, output, and memory. Then the second component is the storage manager, which basically which looks at what are the IO requirements or input output requirements of a given application, how much they are using the different resources or memory at different levels, for example, local memory, remote memory, local cache, or local disk, or maybe shared file systems. So storage manager, the goal is to streamline the IO accesses and provide a fair share of bandwidth to all the users, and it enforces quality of service for IO and provide the stability to the storage systems. The last is the virtualization manager, which performs the curation of software and pastes workloads onto the compute nodes. So virtualization manager enforces quality services by taking inputs from monitoring backend and storage manager. And then it also schedule the workloads onto the supercomputing systems. It also enables complex and rigid softwares to run in diverse environment, which is basically the portability. And this is not easy, as TACC alone has more than 6 different processing and networking architectures. And running an application on a variety of architectures is always challenging. So virtualization manager helps in solving some of these issues, but through the concept of containerization. In detail, virtualization manager consists of two components. The first is controller, or we also say it as scheduler, which basically takes the input from end users. So end users or submit requests to the controller, and even administrators can also interact with the virtual manager, the controller component, to schedule, to first to configure the schedulers, and second to set various environment variables to run it efficiently. Controller in terms receive the inputs from the monitoring component, which basically monitor all the computing resources, and also takes the input from the storage manager to provide a desired quality of service in terms of the I/O for all the workloads running on a given system. So VM controller uses requests workloads to run through the controller scheduler, and scheduler basically controller places the workloads to run on a given HPC system. On the other hand, there is another component called repository, and which basically enables containerization. So containers are a way to run applications with specialized hardware requirements on a variety of software. So containers are kept in the repository, and they are provided to the users when they want to run an application at any build or run times. So containers, in our previous studies, we have run containers up to 8,000 nodes on Frontera systems, and we were able to establish that containers are performant. They run on a variety of hardware and provide an efficient way for users to run their applications. And they are also optimized because the developers of containers integrate their optimal policies within the containers, which would be very extremely challenging for a user to identify. The entire goal of this virtualization manager or this project is, for at least for us, is basically how do we design the virtualization manager? There are several issues, or there are several constraints that we have come through, and we would like to design the virtualization manager that can provide the optimal container performance to all the BigHPC users. So going forward, Sangamithra will present the design alternatives of virtualization manager, and this is basically the designs which we have explored or which we have thought of, which could be serve as a basis for our prototype designs. So I would request Sangamithra to take the control and speak about the various design opportunities that we have explored, and then Om will take over to present what is our current design that we have implemented so far as our prototype design. So Sanga, you can start.
Thank you, Amit. I'm Sangamithra. I'm a second-year master's student at UT Austin, and I'll be talking about the design alternatives that we explored to design our virtualization manager. So primarily, we explored three open source distributions, which were Kubernetes, HT Condor, and Jenkins. Let's get down to the first one, starting with Kubernetes. Kubernetes is an open source system that automates deployment, scaling, and manages containerized applications. And it was primarily designed to shift workloads effortlessly and scale without increasing the amount of manpower involved. As we can see here, this is the Kubernetes architecture. This cluster consists of a set of worker machines that are called nodes that run containerized applications. And each cluster has at least one worker node. These worker nodes then host the pods, which are the components of the application workload. The control plane will then manage the worker nodes and the pods in the cluster. So when we have production environments, the control plane usually runs across multiple computers and a cluster runs on multiple nodes. And this provides fault tolerance and high availability. An example use case of Kubernetes is when BOSS scaled IoT platform as a service running on AWS. And this platform, which included Prometheus monitoring, launched in about 2017 and serves over 3 million connected products from the beginning. So let's now look at why we could not use Kubernetes for our purpose. So these are the limitations we faced. Kubernetes executes kubelets, which are essentially node agents on the compute nodes, and this necessitates a container runtime. Example, container. Container runtime is a low-level component of a container engine that mounts the container and works with the OS kernel to start and support the entire containerization process. The second point is that the container runtime engine necessitates the privilege or root access, which is in general prohibited by HPC administrators. The third point is that Kubernetes also adds an additional layer in the BigHPC framework. And this is kind of difficult to customize, manage, and troubleshoot in the constraints of the HPC environment, which will lead to unreliable behavior sometimes and increased performance overheads. And also, BigHPC doesn't require all of the complex features that Kubernetes offers. So we only needed a subset of that functionality. And to implement it, it would be easier to go ahead with a different approach. So the next approach that we looked at was HT Condor. And HT Condor is a software system that creates a high throughput computing environment. And this was designed to primarily efficiently utilize all available computing resources so that we make use of it in the most optimal way possible. As we can see in the diagram here, it's made up of three components: the scheduler, central manager, and the computing machines. The scheduler is a multi-user client-facing part of the architecture, and it takes care of submitting the jobs, maintaining a job queue, and transferring the input and output files needed for the job from itself to the compute nodes. The next component is the central manager, and this is made up of two daemons: the collector and the negotiator. The collector daemon tracks all the information on the pool, and this can include information about how, when the machines are busy or idle, and which users have idle jobs in the queues. The negotiator then uses this information from the collector to decide which job matches which resources and among which users have the best priority to make use of these resources for their purpose. The daemon that runs in the computing nodes is called startD, and the startD daemon runs on every single compute node in the pool and informs the collector of the machine usage and when it's idle or busy. Once it is assigned a job, it will then contact the corresponding scheduler to start the job. A use case of this would be NASA Advanced Supercomputing Facility, which makes use of it for software development, visualization, email, document preparation, and a wide range of tasks. Let's now look at why we could not go ahead with HT Condor for us. The limitations that we came across were, first of all, it was designed to leverage root access on compute nodes to run specific jobs as different users. Secondly, there was no documentation to use a single non-privileged user throughout the entire workflow. And finally, it only has built-in support for a few container runtimes. And because of all these reasons, we could not use this as well. So the next approach that we looked at was Jenkins. Jenkins is an open source automation server that helps us automate certain parts of the software development process. And this includes building, testing, deploying, and facilitating continuous integration and continuous deliver. Jenkins itself was designed to continuously and dynamically integrate changes into the system as the software development process progresses. As we can see here, this is the architecture of Jenkins. Developers will first commit the changes to the source code, which is found in the repository. And then the Jenkins server checks the repository at regular intervals and pulls any newly available code. The build server then builds the code into an executable file. In case the build fails, the feedback is sent to the developers. Jenkins then deploys the build application to the test server. And if in case the test fails, the developers are alerted. If it finds that the code is error-free, then the tested application is deployed on the production server. So on the left here, we can see the remote source code repository. The Jenkins server will access the primary environment on this left side, and the primary environment can push down to multiple other Jenkins secondary environments in order to distribute the workload. This lets us run multiple builds, tests, and production environments across the entire architecture. Jenkins secondaries can be running different build versions of the code for different operating systems, and the server primary controls how each of these builds operates. As we can see, Jenkins runs on a primary secondary architecture and comprises of many secondaries working for a single primary. This architecture, also called the Jenkins distributed build, can run identical tests in different environments. And these results that are obtained from this are collected and combined on the primary node for monitoring. An example use case of Jenkins would be Twitch, which was developed based on the Jenkins framework. Now, moving on to why we could not use it, we faced two primary issues. One was Jenkins is essentially just an automation language. It's not exactly an orchestrator. So we couldn't use it like for our purpose specifically, and we had to find a way to leverage the automation aspect to design our orchestrator, which was not very possible. The second reason was that it necessitates privileged access on HPC nodes, and this was a problem as we've seen before. So due to these two reasons, we could not use Jenkins either. Now, to summarize, the constraints that we faced for designing the BigHPC orchestrator were, first of all, the design for user space runtime, also no root access. The container engine must not demand root access on HPC cluster nodes because this is in general prohibited by BigHPC HPC administrators. The second point is that we needed a design that was simple and performance efficient for BigHPC users. The third was the design had to be compatible with diverse HPC architectures. And we couldn't use the solutions that we just looked at, like Kubernetes, HT Condor, and Jenkins, because the target sites have incompatible specifications for these approaches that we just looked at. The last point is that we needed a design that provides persistent services for BigHPC workloads, and the HPC compute nodes are hidden from the public network. For our case, that would be the orchestrator. And we needed a mechanism that could reach these nodes from public networks. So therefore, we needed a design where the compute nodes tell the orchestrator their availability, and then the orchestrator runs based on this information. So in light of all of this, we decided to go ahead and build our own orchestrator, our own indigenous framework. And Om Saran will now talk a little bit about this and tell you how we went about going.
Om, can you share your screen?
Hi, I'm Om, a master's student at UT Austin. I'm going to today talk about the BigHPC orchestrator, specifically the intermediate prototype that we have implemented. So the goal of the intermediate prototype was to come up with an orchestrator that takes care of some constraints like the unavailability of root access in HPC sites, and the network communication that Sangamithra had spoken about, where the compute nodes are in a private network. We'll talk more about this in the coming slides. And also to easily integrate with existing HPC sites and the workload managers that are already present in the HPC sites. That's what we'll be talking about. And like the things that we will be covering as part of it is, first, we'll talk about the system architecture of the orchestrator. Then we'll see how a user submits his workload. The workload can be something like a scientific experiment that a scientist wants to run on the BigHPC framework. Then we'll see how a node is reserved for BigHPC so that the BigHPC framework can start using the compute nodes available in the HPC. We do something known as the node reservation so that we can easily integrate with the existing HPC infrastructure that's already present. Then we'll see once the nodes are reserved, how the nodes are initialized and before it is ready to use for the BigHPC applications. Then we'll also see how the workloads which are submitted by users, how they're scheduled and dispatched onto the compute nodes and executed. Yeah, so that's what we'll be looking at today at a high level. So first, let's start with the system architecture. So as you can see, we have multiple infrastructure components over here. So in the private network that we discussed, we have the HPC cluster, and there are a cluster of compute nodes. This is where the actual program that the user specifies ends up being executed. They're in a private network. This implies that we cannot access these nodes directly from over the internet. Then on the right-hand side, in the public network, we have a BigHPC virtual machine. This virtual machine and the services running inside this can be accessed over the internet and are publicly available. This means that multiple HPC sites can access the BigHPC VM services via the internet. Then we have the repository database that Amit had spoken about. We reuse the same database for the Orchestrator services that run. And also we have the command line interface tool, which are basically used by the end users and the BigHPC administrators. By BigHPC administrators, they use it to configure the BigHPC Orchestrator, and end users use it to basically submit their workloads. Within this infrastructure, we have some services which are required by the BigHPC Orchestrator. So in the compute nodes that we are talking about, we have something known as the executor service, which runs, and its primary responsibility is to communicate with services running in the BigHPC VM, and also to execute the user workloads that the user has submitted on that particular compute node. Then in the BigHPC VM, we have the controller, which Amit had previously described. Its main responsibilities are to basically schedule the user-specified workloads on the appropriate compute nodes. And the job of the dispatcher is to basically, once it's scheduled, dispatch it onto the compute nodes and run them. So this is what the architecture overall looks like. Now we'll see how a user actually submits a workload, for example, his scientific experiments that he wants to run on the via the BigHPC framework. So the user interacts with a command line interface tool, and via this, he basically specifies his job arguments. For example, the number of nodes that he wants to use, the kind of hardware that he needs to run his workload. For example, he might require a GPU. Then once that is submitted to the command line interface tool takes care of creating a job entry in the repository database that we previously discussed. And the job basically can be in multiple states, in pending state, which means that it has not yet been scheduled. And it also has other states like running, which means that it is currently being executed, and also some terminal states like completed, which means that the job has completed its execution. So this is how a workload submission is done. The user specifies his or her job arguments via the command line interface, and an entry is made in the BigHPC Orchestrator. Next, we'll see BigHPC reservation. So we spoke about how we need to use the existing HPC workload managers to run the BigHPC Orchestrator. One example would be TACC, and TACC we use Slurm as the workload manager, and the BigHPC framework needs to run on top of the existing workload manager like Slurm. So the way it is done is we have the BigHPC VM running in the public network, and HPC sites usually have something known as the login nodes, which is usually in the traditional sense, it is used by the users to log into that node and basically create reservations so that he can execute his or her workload. So in this scenario, since the user will be submitting the workloads via the BigHPC framework, what BigHPC does is it logs into the login node as a BigHPC user, and then invokes a script which is present in the login node. What this does is it creates a reservation for the BigHPC use case. It basically reserves a bunch of compute nodes, which is configurable. For example, if like 10 nodes are required, then it will submit a request for 10 nodes. Yeah, and this script, what it does is it reserves the compute nodes and also takes care of starting the services which are required by the BigHPC Orchestrator. As we saw in the previous slides, the compute nodes require the executor service. So this is how a BigHPC reservation is done. This reservation mechanism allows not just integration with Slurm, it also allows integration with other workload managers like PBC. Yeah. Then once the nodes are reserved, we'll see how it gets initialized before it can be used to run the BigHPC workloads. So as we saw previously in the private network, we have a bunch of compute nodes, and now that they have been reserved and the executor has started, we'll see what the executor does as soon as it starts. So the first thing the executor does is it initiates a bidirectional WebSocket connection with the service in the BigHPC VM, that is with the dispatcher. This connection is initiated from the executor because it cannot be initiated from the dispatcher as it is in the private network. So that is how we solve this issue. And this bidirectional connection will be used for future communication between the compute nodes and the BigHPC controller. Yeah, so once it establishes the WebSocket connection, what it does is it registers itself as a node available to be scheduled with the BigHPC orchestrator. It does that by basically communicating with the dispatcher and invoking an RPC call, saying that giving the hardware information and the reservation information to the dispatcher. And the dispatcher basically makes an entry into the database saying that a new node is now available for scheduling. So this is how nodes, the compute nodes in the HPC cluster are initialized and ready to be used by the BigHPC framework. Then we'll see how the jobs that are submitted by the users scheduled. So in the previous slide, we saw that when the user submits a workload, it gets registered in the repository database in the pending state. So what the scheduler in the controller does is it keeps polling for pending jobs, and then it searches for the nodes that can satisfy the job's requirements. For example, the job may require a GPU. So when it searches for nodes for that job, it will search and it will make a query in such a way that a GPU is present in that node. So that is what it queries for here. And then, but if the node is actually, if a satisfying node is not actually found, what it does is it basically creates another reservation that we saw previously in the slides. And once it finds the appropriate nodes for the job, it basically creates an entry in the job queue. Basically, it has a mapping of a job and what all nodes it needs to be run on. So this is how jobs are scheduled. And this job queue is currently implemented in memory. And this memory is basically shared between the scheduler and the dispatcher, as we'll see in the next slides. So now on to dispatching the jobs. Now the jobs that have been scheduled need to run on the executor. We'll see how that is done in this slide. So previously we had seen that once a job is scheduled, it's added into the job queue. And then now we have the dispatcher, which basically polls for scheduled jobs. And once it finds a job that has been scheduled, it basically needs to send this information to the appropriate compute node so that the job can be executed. So that it sends the job details from the dispatcher to the executor. And then the executor starts running the job. And once it's complete, it sends back the output and the logs of the job back to the dispatcher so that the user can see. So, so this is how jobs that are scheduled is dispatched onto the compute nodes, executed and returned. So yeah, so this is how at a high level the orchestrator works. It allows the user to basically run his workloads without root access and things like that. So in summary, we have seen that the design that we've come up with for the intermediate prototype enables us to overcome some constraints. Like, for example, integrating with the HPC workload managers, which are already existing, for example, Slurm and TACC and PBS, LSF, etc. This is generic, and the mechanism of BigHPC reservations allows us to basically easily integrate. And also it helps us overcome the networking limitations that we had discussed. We do not require a public network for the HPC cluster compute nodes, basically. Yeah, and it also, via the controller and executor components, we are able to run the user workloads without root access. So this is what the Orchestrator intermediate prototype looks like. And to see what we're going to further do with it, I'll invite Stephen to talk about that. Yeah.
Great.
Yeah.
Thank you. So what I'm going to talk about next is basically our next steps. And with this design, we found we actually had a really productive discussion with our group 2 weeks ago, or maybe last week, who can tell. But through that meeting, these will be our next steps to integrate with all of our different collaborators. So first of all, we're going to use the same database, and that we need to start to do that. Design-wise, the executor will run a few, as soon as the allocation begins, the executor will run a few persistent services, things that are not job specific, such as monitoring or the data control plane. Those need to be persistent for the life of the allocation, and so we'll be executing those. And also we'll be making sure that in order for all of the components to work together correctly with the shared database, we'll have the BigHPC job IDs there. Also on the docket will be new scheduling algorithms, and Sangha will be working on those. Right now, we just have a very basic algorithm, which is first come, first serve, but I think we'll at least get some other algorithms such as fair share and things like that for our next steps. Can you go next? There we go. So this is just kind of a recap of some other work that Amit and the rest of the team have done. And some reminders. So HPC and big data don't coexist easily. We've shown that the virtual manager can provide portable and optimized containers. And using those containers, we've shown that we can provide software level portability and provide containers for each system. Also in some previous work and in a previous webinar, if you'd like to check, we talked about validating the performance overheads for the machines with containers, and we have found that there's very little overhead and in general no major security issues with using these containers. And so with this entire design, we've shown how we can use these portable and performant HPC containers within typical everyday HPC clusters that exist all around the world from a central BigHPC scheduler. And I think we've shown that we are on the path to have a good product to do that. And now, any questions or about any of the slides or anything like that? Okay, if there's no questions, Miguel, do you want to take over?
Okay, so I think we can start the discussion time. I'm not sure if we have any question on the chat. Again, feel free to ask your questions on the chat, and we will discuss them. So maybe I can do a question. How do you deal with heterogeneous hardware to support application containers? Does containers built for x85 machines work on IBM Power 9 platforms?
No, you have to build for each architecture, unfortunately. So we do have some good instructions about putting performant applications that have specific, requirements such as GPUs or MPI versions. So we provide those instructions, but ultimately, if they use a specific piece of hardware, it can only be used. The drivers have to match what is being used on the hardware. So maybe you get a situation where there's multiple machines with, the same versions of MPI, and that would be reusable. But if the hardware is different, we don't have much of a choice. However, we do have a few ways that we can support multiple architectures within one container, and we've been exploring that. But as of today, you really have to just build the correct drivers for the correct machine.
Okay, thank you. And what scale have you tested containers, and what overheads have you seen?
Yeah, this is quite a good question. So we had a paper in ISC, and we tested containers at 6,000 nodes on Frontera system. And recently, in the last exascale days, we have increased that limit to 8,000 nodes, which is basically almost 400,000 containers. And we have found like containers have minimal overheads. And those overheads, even if it is small, few seconds compared to the bare metal runs, they don't matter, because the scale at which you are running the containers and the feature that containers provide, which is basically portability, the user doesn't have to worry about reinstalling all the applications from scratch and spending a lot of time. So that a huge amount of time is saved just using the containers, and the way they run on performantly on our systems, it shows they have a huge potential. And even developers can integrate their own specific optimizations within containers, which any user can leverage and run containers very efficiently on different systems.
Okay, thank you. So I'll ask the audience if anyone has a question. Please feel free to share that question with us. Otherwise,
so I would ask audience if they have any suggestions. Like, we have come up with a design, our own designs, which basically implement the virtualization manager. But we have explored other solutions, Jenkins, Kubernetes, and HT Condor in past. If you have any suggestions, like which is more efficient, or you want to find out some features from our virtualization manager, feel free to let us know, even with this presentation, or even you can send us an email. We can have a discussions with you, or we can come up with something which is more efficient what we have right now.
okay, it seems that we have here a question from João Paulo. Since we are,
I can make the question. I can ask the question here. I was just putting on the chat. You can hear me, right?
Yeah,
yes.
right.
Okay. Thank you for the presentation. So, since you were discussing about scalability, I'm going to ask the same question, but for the architecture you showed for scheduling jobs and all the things you presented in this final solution that Tom presented. So for large deployments, large reservation of nodes, lots of jobs or containers running in this BigHPC infrastructure, do you see any scalability challenges, any specific points that may create contention if we want to scale this for a large number of nodes and jobs? Do you have you thought about this? Do you have any idea?
So definitely there will be issues. I mean, running containers. I tested just running one container on large number of nodes. That was working fine. But when you run multiple containers or multiple users share the file system, so different issues will arise because everyone may try to access or abuse the system shared file resources, and this is where our other components come into picture. For example, storage component, which is basically a layer to streamline the access. If someone is using a lot of access, then we can streamline or we can reduce those IO accesses. Similarly, if basically the monitoring agent providing us the feedback of quality of service, and then or even users can specify what quality of service they want, and we can verify those requirements before the containers actually run on the system. So we can limit those requirements, and then even if those requirement needs to be met, then other components comes into picture and improve the or provide the fair share access of different resources for different users. So yeah, definitely there will be issues, but those issues will be resolved by other components.
Okay, thank you.
Miguel, you have your mic on mute.
Sorry. So, as I said, since there are no more questions from the audience, it is time to close this webinar. Thank you for your participation and for your questions. I'll take this moment as well to thank all the speakers for those excellent presentations. Please stay tuned for the next webinar, which will take place in November 17th, 2022, with Julio Costa from Wavecom, who will talk about monitoring in BigHPC lessons learned. And thank you for joining us.
Thanks, everyone.